All right, so all else being equal, nucleophilicity increases with basicity, right? So hydroxide is a better nucleophile than water. Hydroxide is a much stronger base. You've got the same nucleophilic / basic atom, basically the same size, but hydroxide's a much stronger base, so it's a better nucleophile than water. But there are quite a few molecules that are good nucleophiles without being especially strong bases. Cyanide is one of them. Kind of the related azide, and both of those molecules are quite toxic. I don't know. I actually don't know. I've never done a lot of biochemical work, but I know we used to keep buffers. If you don't have to work with cells, anything that's going to be alive, it was pretty common to sort of keep a little bit of azide in your buffer because that would keep mold from growing in it, right? It's a preservative. Azide's toxic to most things. In the same way that cyanide is. So cyanide and azide both are toxic to humans. They bind hemoglobin really tightly, and that's a nucleophilic reaction. So you've got this electrophilic iron. Cyanide or azide come in and bind that, and the way it's supposed to work, oxygen comes in and binds that, but really weakly, and so it can come back off. Cyanide and azide both go on there and just stay, so they're not good for you. Phosphines. The other thing you should know is nucleophilicity increases as you go down the periodic table. So amines are good nucleophiles, but they're also strong bases. If you go down a row, you get to phosphines. So phosphine is going to be a better nucleophile than nitrogen. It's actually going to be a worse base, a weaker base. All right? The same thing then is true of thiols, and even neutral sulfurs are pretty good nucleophiles. And what this is really doing is talking about polarizability. So when the valence electrons are farther away from the nucleus, they're more susceptible to passing electrophiles, right? So you go down a row from oxygen, you get to sulfur. So SH minus is a much better nucleophile than hydroxide, even though it's a much weaker base. And then keeping in that spirit, selenium. You don't see a lot of selenium chemistry, although we have a guy here in the department at Wake Forest. He's actually downtown at IQ, who does a lot of selenium chemistry. Selenium medicinal chemistry, some really neat stuff. And then, kind of oddly, iodide and bromide are actually pretty good nucleophiles, right? They're good leaving groups. This still to this day blows my mind a little bit. Iodide is a really good leaving group. It's pretty much the best leaving group we talk about in Orgo 1. It's also it's a really good nucleophile, right? It's very polarizable. The valence electrons are way out away from the nucleus, and so it's both a good leaving group and a good nucleophile, which does some interesting chemistry. There are others. I think there's I've got a list somewhere. I think it's in the chapter 7 module of things that are good nucleophiles, like lists of nucleophiles. Should take a look at that, and it's also in the textbook. Anyway, this particular reaction, we have cyanide, which is a really good nucleophile and a fairly weak base. It's a relatively weak base. All right, so I'm going to let you, if you want to think about that, maybe that changes your answer. Go ahead and take a moment. All right, I should have done this. What kind of carbon is the leaving group on? Secondary. So this is a secondary alkyl chloride. Okay, so in a secondary alkyl chloride, we have all of the mechanisms available to us. Especially in this one, where the cation you would get if the chloride leaves would be resonance stabilized. So it's secondary. Secondary cations aren't all that stable. They form, but they're not that stable relative to other cations. But this one is also stabilized by resonance from the benzene ring. Okay? So secondary, like tertiary chloride or tertiary carbons with leaving groups, no Sn2 is possible. Sn1 and E1 are pretty good. Primary, if there's a methyl group with a leaving group, like it can't do elimination. There's no beta carbon. Can't do Sn1 because it can't make a cation. So that directs you straight to Sn2, no matter what the base and nucleophile is. Here, with the secondary, you got to kind of consider all of it. Okay, over here then, we got a good nucleophile, but not a strong base. This really suggests Sn2. All right, so E2 is driven by a strong nucleophile, or a strong base. We don't have a strong base, we've got a good nucleophile. And so I'm going to draw you the product down here. And then I'll talk a little bit more about this reaction, some stuff that some weeds you can get down into. So Sn2, if the nucleophile does an Sn2 reaction, you're going to see inversion of configuration on that carbon. But only on this carbon, okay? So the mechanism here is going to be the cyanide displacing the chloride. A rule of thumb is, it's not really a rule of thumb, it's an ironclad, never violate this rule. So if there's not an arrow to or from an atom in a mechanism, nothing happens to that atom. Nothing changes on that mechanism. The arrow is going to tell you everything that changes. I also uploaded not an assignment, but a practice sheet. If you're having trouble with curved arrows, it's just a mechanism practice sheet, and there's a key with it that you can play with. But this mechanism, the cyanide displacing the chloride, right? We figured out it's an Sn2 based on all this structural stuff, so that's our mechanism. We're going to invert the stereochemistry at the alpha carbon. We're not going to touch this chiral center over here. So nothing happens to that thing. It stays as it was. Okay. Any questions up to that point on this reaction? Yeah.
Could you actually draw the mechanism for the last one? Just the arrows?
Yeah, no, I can do that. I will come back to that. Any questions on that Sn2 before we move away from it for a second? Okay, so the mechanism over here, look at this. The methoxide is going to be a base. It's going to grab that hydrogen. So the minus goes to the hydrogen. I've looked at 7 or 8 of the acid-base problems. You really want, the arrow to end on the atom the bond gets made to. Like out of those 8, 2 or 3 of you drew an arrow, like if there's an OH that's acidic, 2 or 3 of you drew an arrow to the O. Right? You drew the right products, but the arrow went to the wrong place. So this O makes a bond to the H, the CH electrons make the pi bond, and then CBr electrons become a lone pair on the bromide. So those purple arrows are the mechanism. Okay. So back on the E2 reaction. There are a couple of things here, and one was asked about. So what is the DMSO doing? The DMSO is solvent. so solvent and temperature, if you look at the flow chart in the chapter 7 module, solvent and temperature are down way at the end, and they should always be at the end. The solvent and the temperature is not going to tell you, it's not going to be dispositive for which mechanism's happening. It'll tell you relatively how fast the mechanism happens. So for an Sn2 reaction, well, we've got, I'm trying to think how best to, we've got several different, polar protic solvents first. Protic, so DMSO has hydrogens in it. Right, if you look at this, 6 hydrogens, 3 on each methyl group. So you might think that's a protic solvent, it's got protons in it. But a protic solvent means hydrogen bonding. All right, so a solvent that is polar and can be a hydrogen bond donor is called a polar protic solvent. Polar aprotic solvent has no hydrogen bonding. And then we've got nonpolar solvents. And we are going to make the assumption that there's no hydrogen bonding here as well. Right? If it's a nonpolar solvent, it's not going to be a hydrogen bond donor. Pretty much, if it can be anything that can be a hydrogen bond donor is probably going to be polar. So some examples. Give me an example of a polar protic solvent. Ethanol is good. If this was the Family Feud, that would be at least answer 1 or 2. Let's say it's answer 2. What's answer 1? Water. These make a nice combo. End of a long day. All right. Ethanol and water are polar protic solvents. They're polar. They hydrogen bond. Methanol is a polar protic solvent. Isopropanol, N-propanol, butanol. Pretty much any solvent that's got an OH or an NH. All right, any solvent that's got an OH or an NH in it will be good. All right, give me an example of a polar aprotic solvent. Yeah, DMSO. It's the one I've written over here. So DMSO is a good one. And actually, so there are scads of these. Okay, so DMSO, DMF. Acetone. These are the 3 I'll use. I've given the structure of DMSO over there. Dimethylformamide. So it's got an aldehyde, a nitrogen that's got 2 methyl groups on it. Acetone has a carbonyl, 2 methyls. So acetone's sort of the carbon equivalent of DMSO. How about a nonpolar solvent? Hexane, good. Pretty much went to, that's about as nonpolar a solvent as you can find in an organic lab. Okay, so which solvents go with which reactions here? And if you look at this, a polar protic solvent, you might think, well, that should be the best. It's really polar. The transition states for an E2 and an Sn2 reaction are polar. So as you think about a chemical reaction, right, you got a rate limiting step. I guess we could draw this wherever. We've got one step, right? You can accelerate the reaction by doing either of those things. So we can destabilize the reagent. That is, we can make the reagent or the reactants more reactive. That'll accelerate the reaction. That's by definition what you're doing, right? If I say a reactant's more reactive, I mean it reacts faster. The other way to accelerate a reaction is to lower the energy of the transition state. Okay, so if the transition state is polar, putting that in a nonpolar solvent will actually destabilize it. Right? Like dissolves like, that really simple thing you learn. So if I've got a reaction that has a polar transition state, I want a polar solvent for that. So for all these reactions, non-polar solvents aren't going to be real useful. Reactions, all four of these mechanisms will be slower in a non-polar solvent than they would be in a polar solvent, right? Because the transition state's destabilized. So then, based on that, based on the transition state, you might think the polar solvents, protic or aprotic, won't make any difference to the transition state, and that's generally true. But think about what has to happen. So over here, I'm going to erase some of this stuff now. All right, here's a product. So in this reaction, right, that cyanide is going to react. It's a Lewis base. It's an electron donor. So we want it to be more reactive. We would like that cyanide to be as reactive as possible. If we put this in a protic solvent, let's say we do this reaction, let's do this reaction in ethanol. Right? Ethanol can hydrogen bond to the lone pairs on that cyanide. By hydrogen bonding to the cyanide, we're going to stabilize the cyanide. That makes sense? All right, so if we stabilize the cyanide, we're going to make it less reactive. The reaction will be slower. So it turns out Sn2 and E2, because they're driven by the base, in a protic solvent, Sn2 and E2 are slower than in an aprotic solvent. I erased my DMSO. Silly. All right, so there's DMSO. It's not a hydrogen bond donor, so it can't stabilize the cyanide. It can stabilize the potassium. Right, that O can interact with the potassium, kind of pull the potassium away from the cyanide. The cyanide's a little more naked, it reacts better. So in aprotic solvents, Sn2, E2 are faster than in, I've already written this. Same sentence, just in a different line. Okay, in an aprotic solvent, Sn2 and E2 are going to be faster than in a protic solvent, in a space protic solvent. All right, and it all comes down to hydrogen bonding. The E2 and Sn2 are driven by the base, driven by the anion, driven by the thing with electrons. If those electrons interact with the solvent, they're going to be more stable, they'll be less reactive. Now, think about the Sn1 reaction. The slow step of the Sn1 and E1 is the leaving group leaving. Right, so now we want to either destabilize the reactant or we want to stabilize the transition state, the intermediate. And now a protic solvent works out really well. Right? The chloride can hydrogen bond to the water. I just got through, you all nodded and said you understood that a protic solvent is going to stabilize the anion. So here, stabilizing that anion actually speeds the reaction up. Okay, so up here, protic solvents. A protic solvent will accelerate an Sn1-E1 reaction relative to the same reaction in an aprotic solvent. Fair enough? Okay, so here's the thing. That is a really subtle effect. That's an effect on the rate of the reaction. That is not going to tell you which mechanism happens. And that maybe gets down, like I said, if there's a secondary, if you have a leaving group on a secondary carbon, and it can kind of do all four of the mechanisms, it's possible that in one solvent it would be mostly Sn2, and in another solvent it would be mostly Sn1. But most of the time, the fact that it's a primary halide, or you have a good nucleophile, or a strong base, that's what's going to take you to the mechanism you need to do. And now you're just kind of judging rate, right? So this E2 reaction would actually be faster if instead of running this in methanol, we ran it in DMSO or DMF. But it still would happen in methanol. It would just be a little slower. And it's a good reaction, so it doesn't really matter. It can't do an Sn2. There's not really any reason to go to the trouble of making your sodium methoxide in DMSO rather than just in methyl. All right, and then the last thing, let's just do it. Let's just do a new reaction. How about that? The last thing is temperature. Come down to the temperature next. All right, product and mechanism.